Okay, now we continue to learn Chapter 5, Orthogonality. Section 3, Least Squares Problems. Part 1, Least Square Solutions to Overdetermined Systems. Okay. So, a standard technique in mathematical and statistical modeling is to find a least squares fit to a set of data points in the plane. So, this technique is introduced by Gauss. So Gauss is gives very useful way to find a least squares fit to a set of data points. So given the data points xi, yi, we seek this problem. We try to minimize f of xi minus yi length power 2 such that f belongs to this set of functions. So this C is a fixed class of simple functions, maybe linear function, maybe quadratic function, maybe cubic function. Okay, yi is the data you know already. Should be this one, right? Observe the data here, and so which f is the one that fits this data best. So the definition, residual and least square solution. Given a system of equations Ax equals b, where A is an n by n matrix with m greater than n. So m greater than n, so this is an overdetermined system. And b belongs to Rm. Therefore, each x belongs to Rn, we can form a residual here. Rx equals b minus a times x. If this overdetermined system has a solution, then of course the range of x should be 0. Right? Ax equals b, the range of x equals 0. But because it is we already consider overdetermined system, so we may not find a solution satisfy all the equations. So in this case, you will have non-zero residual. The distance between b and ax is given in this way. You can use length of b minus ax, which is the length of the residual Rx. So the length of residual is the distance between b and ax. So we wish to find a vector x in Rn for which the length of Rx will be a minimum. So we minimize length of Rx is equivalent to minimizing the length of Rx power 2. They are the same, right? A vector x hat that accomplishes this is said to be a least square solutions to this system Ax equals b. Clearly, p equals a times x hat. So it is in range of a is closest to the given vector b if exists. See, you try to minimize length of Rx. So that means you try to find p equals ax hat, which belongs to the range of a that is close to the given vector b. So consider about this. First, we have this theorem 5.3.1. Let S be a subspace of Rm. For each b belong to Rm, there is a unique element p of S in this subspace that is closest to b. That is, for any y does not equal to p in this subspace, the length of b minus y is greater than the length of b minus p. So this p is the unique element you find that is close to the given vector b. Furthermore, a given vector p in S will be closest to a given vector b belong to Rm if and only if b minus p belongs to this orthogonal complement of S. So we see the proof. Because Rm, this m-dimensional Euclidean space, can be written as a direct sum of S and its orthogonal complement. Okay, and this means for any vector b in Rm, it can be written in two paths, addition of two paths. First one is P, where P belongs to the subspace S. The second part is Z. This vector Z in S orthogonal complement. If Y is any other element of S, then we have B minus Y length power 2 equals B minus P plus P minus Y length power 2. This is obvious, right? You minus P plus P here, so they are equal, right? And if you have this length power 2, then you can write, because P minus Y in S and B minus P in S orthogonal complement. So we have a B minus Y length power 2 equals B minus P length power 2 plus P minus 1 length power 2. Then you have a B minus 1 length greater than B minus P length, because this one is non-negative, right? P and Y. Okay, this one is greater than 0. Let's see the proof. Because any m-dimensional, this m-dimensional Euclidean space can be written as S direct sum with S orthogonal complement, and then you can write B, this m-dimensional vector, as P plus Z belongs to Rm, and P in S and Z in S orthogonal complement. If Y is any other element of S, this means Y and P, they are not the same, right? Y is any other element of S, then we know that the length of B minus Y power 2 equals B minus P plus P minus Y length power 2. This is the equivalent transformation. And because P belongs to S and Y belongs to S, and S is the subspace, so P minus 1 belongs to this subspace. And also because B minus P equals Z, where Z belongs to S orthogonal complement. So we know that this vector B minus P and this vector P minus 1, they are orthogonal. By the Pythagorean law, we know that length power 2 of B minus 1 equals length power 2 B minus P plus this length power 2 of P minus Y. So because P and Y, they are not the same vector, so its length is greater than 0. Therefore, length of B minus 1 greater than length of B minus P. Thus, if P belongs to S and B minus P belong to S orthogonal complement, then P is the element of S that is closest to B. Conversely, if Q belongs to S and B minus Q does not in S orthogonal complement, then we know that P does not equal to Q, and it follows from the preceding argument that the length of B minus Q is greater than the length of B minus P. We give a name for this vector P. We call it a projection of B onto range of A. It follows from theorem 5.3.1 and theorem 5.2.1 that B minus P equals B minus AX hat equals the residual RX hat. So RX hat belongs to the orthogonal complement of range of A. Okay, and by the fundamental theorem, we know that fundamental subspaces theorem that the orthogonal complement of range of A equals the null space of A transpose. So we can see from this figure, we see this B belongs to R2, so it's a vector here, and A is a 2x1 matrix of rank 1. So the range of A is just this line, and we know that P is this vector. This is a projection of B onto RA, and RX hat is this vector. It belongs to the range of A is a complement, right? Orthogonal complement, which also equals the null space of A transpose. Okay, if in three-dimensional space, we can also have this figure. Okay, B here belongs to R2, two-dimensional vector, and A is a 3x2 matrix of rank 2. So the range of A is a plane here, and if you have B here, then its projection P is here, okay? It's Rx hat also belong to the orthogonal complement of range of A, which is in the null space of A transpose. Okay, then from this theorem, from this result, you want to know how to compute this P, right? How to get this projection vector. Okay, so a vector x hat will be a least square solution to this system Ax equals B if and only if Rx hat belong to the null space of A transpose. See, because Rx hat belong to null space of A transpose, we know that A transpose times Rx hat should be 0. And Rx hat equals B minus Ax hat. So you have A transpose Ax hat equals A transpose B. So if you get the solution of this equation, you will get this vector x hat. So this is a least squared solution to this linear system. And we give a name for this equation as a normal equation. So theorem 5.3.2, if A is an n-bar matrix of rank n, the normal equations A transpose Ax hat equals A transpose B have a unique solution. X hat equals the inverse of A transpose A times A transpose B. And X hat is a unique least square solution to the system Ax equals B. The proof can be seen from this page of the textbook. And in fact, it's very easy to show that because A is an n by n matrix of rank n, so you know A transpose A is a matrix n by n matrix of 4 rank. So it's rank n, so it has an inverse. Then, of course, X hat equals this inverse matrix times A transpose B, which is unique. Okay? So X hat is a unique least square solution to the system Ax equals B. And the vector P is called the projection vector, which equals A times X hat equals A times A transpose A inverse times A transpose B. So this is an element of range of A that is closest to the vector B in the least squared sense. And the matrix P is called the projection matrix, where P equals A times A transpose A inverse times A transpose. We just denote this matrix before B as the projection matrix.